Welcome to our quantum deep dive. Today, we're jumping into one of the most mind-bending, rule-breaking ideas in all of physics, Bose-Einstein statistics. It really does rewrite reality as we know it, and this entire deep dive is inspired by a brilliant essay from Jorg O. Scheppet. So let's get into it.
You know, we all learn this rule as kids, right? You can't walk through a wall. Two objects can't be in the exact same spot at the exact same time. But what if that's not always true? What if, down at the tiniest, coldest scales imaginable, that fundamental rule just breaks? We're about to enter a world where particles don't just share space, they actually love to, creating some of the wildest things in the entire universe. So here's the plan. First, we'll figure out why we even need a whole new set of rules for quantum particles. Then, we'll meet the two major families that make up the quantum world. They have very different personalities. We'll dig into the amazing story of Bose and Einstein's collaboration, see the bizarre effects their theory predicted, and finally, look at how this is literally building the technology of tomorrow. All right, first up, why bother with something called quantum statistics? Well, it's because the physics that works so well for, say, a baseball just completely falls apart when you get down to the atomic level, especially when things get incredibly cold. The old rules treat particles like tiny individual billiard balls you can track, but in the quantum world, that's just not how it works. We need a whole new playbook. And this right here, this is the absolute heart of the matter. In our world, you can put a little chalk mark on billiard ball A and billiard ball B, and you can always tell them apart. But in the quantum world, two identical particles, like two electrons, are fundamentally, completely, utterly indistinguishable. You literally can't tell which is which. And this isn't some minor detail, it changes everything. The question is no longer which particle is in this energy state. The only question that makes sense is how many particles are in this state.
Okay, so once you accept that particles can be totally identical, it leads to a huge split in the quantum world. It turns out all particles fall into one of two major families, and each family has its own unique personality, its own set of rules for how they behave when they get together in a crowd.
First, let's meet the bosons, named for the physicist Sachendra Nath Bose. These are the social butterflies of the universe. They have a property called spin that comes in whole numbers, 0, 1, 2, and so on. The key thing about them is they have absolutely no problem piling into the very same quantum state. You can think of a quantum state as a particle's unique address and job description, its energy, its momentum, all of it. And bosons, they love to share that address.
And then you have the complete opposite, the fermions, named after Enrico Fermi. These guys are the antisocial loners of the particle world. Their spin comes in half integers, and they are fiercely individualistic. They live by a super strict rule called the Pauli exclusion principle, which basically says no two of us can ever be in the same state at the same time. They always demand their own personal space.
So let's just put it all together. Bosons are the social particles that can all pile into one state. Think of photons, the particles of light. Fermions are the individualists that build the solid stuff around us because they refuse to share space. These are your electrons and protons. This single difference is why solid matter exists, but so do things like laser beams. It all comes down to their social behavior.
Now, this whole idea didn't just pop into existence. It's actually the result of one of the coolest and most unexpected partnerships in the history of science. It's a story that starts with a paper that nobody wanted to publish and ends with the prediction of a totally new form of matter.
It all kicks off in 1924. An Indian physicist named Satyendra Nath Bose figures out a radical new way to describe light by treating photons as truly indistinguishable. But the big physics journals in Europe, they rejected his paper. So in a move of sheer confidence, Bose mails it straight to the most famous scientist on the planet, Albert Einstein, and Einstein gets it. Instantly, he sees the genius in it, translates it into German himself, and uses his own massive reputation to get it published. But he didn't stop there. He took Bose's idea and ran with it, predicting that if this works for photons, it should also work for atoms, and if you get them cold enough, they should all collapse into one single bizarre quantum state.
And you just can't overstate how huge this was. Before this, statistics was all about counting separate, individual things. Bose and Einstein came up with a way to describe a system where the things themselves could completely lose their individuality and just merge into a collective. It was a completely new way to even think about what matter is.
Okay, I know this might all sound super abstract, but the consequences of this social particle behavior are incredibly real. And not just real, but visually spectacular. This isn't just math on a whiteboard. It's the recipe for some of the most amazing and strange things we've ever seen.
There are three huge phenomena that are born directly from this idea.
the perfectly focused power of a laser, the strange frictionless flow of something called a superfluid, and the ultimate quantum state of matter, the Bose-Einstein condensate. Every single one is a direct result of bosons deciding to act as one giant team.
Think about a simple laser pointer. That perfect, intense little dot of light, that's a quantum crowd in action. Every single photon in that beam, and they're all bosons, is cooperating. They are all in the exact same quantum state, with the same energy, the same direction, the same everything. They're marching in perfect lockstep, and that's what makes laser light so different and so powerful compared to the chaotic jumble of light coming from a normal light bulb.
But it gets way weirder when you look at atoms. A helium-4 atom, it turns out, acts like a boson. And if you cool liquid helium down to just below 2.17 Kelvin, we're talking minus 271 degrees Celsius, something incredible happens. It becomes a superfluid. All the atoms merge into a single quantum state, and the liquid can flow with absolutely zero friction. It can literally crawl up the walls of its container and escape, all because of its collective quantum nature. It's wild.
And now for the grand prize, the state of matter Einstein predicted way back in 1925 that we couldn't even create until 1995, a Bose-Einstein condensate. To make one, you first hit a cloud of atoms with lasers to slow them way, way down. Then you trap them with magnetic fields. The really clever part is the last step. You let the hottest, most energetic atoms escape, which makes the whole group even colder. It's just like how steam rising from your coffee cools it down. Finally, at just billionths of a degree above absolute zero, the atoms give up. They stop being individuals, their identities blur, and they condense into a single quantum object, a superatom.
Now, this isn't just about exploring bizarre physics anymore. Our ability to control these quantum crowds is now the foundation for a whole new era of technology. We've moved from just observing these effects to actively engineering them to build things we could only dream of before.
So what's in this new toolbox? Well, you've got quantum computers that use photons to tackle problems that would take a normal supercomputer billions of years. You have quantum communication, using photons to create truly unhackable networks. Scientists are using BECs as controllable little universes to design new materials from scratch. And we're building sensors with these condensates that can measure things like gravity with an almost unbelievable precision.
And this is not science fiction. It's happening right now. Just look at quantum communication. In 2016, a Chinese satellite named Mikius successfully beamed entangled photons, which are bosons linked together by quantum weirdness, down to Earth over 1,200 kilometers away. This was a massive first step towards a global, ultra-secure quantum internet, built entirely on the behavior of these social little particles.
So, when you pull it all together, it's an incredible story. It started with a single, rejected scientific paper and has completely reshaped our world. Bose-Einstein statistics pulls back the curtain on a deeper reality, one where it's not about individual parts. It's about collaboration, where particles merge their identities to create things far, far greater than themselves.
Which, of course, leaves us with a pretty exciting final question. We've learned how to see these quantum crowds, and now we're learning how to control them. As we get better and better at conducting this quantum orchestra, what new realities, what new technologies, what new truths about the universe will they unlock for us next? And that's our deep dive on the quantum crowd. This whole explainer was based on the fantastic work of Jörg Schneeppot. If you want to go even deeper, check out his website at schneeppot.de. Thank you so much for joining us. Goodbye.
Schneeppot.de is a private project by Jörg Schneeppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.